Okay, so the next talk is the shadow bands atmospheric research for the upcoming solar eclipse that's happening in April.
In October.
Oh, October. Oh, it's October.
The annual eclipse.
Oh, the end. You're going to do the end. Okay, cool. So we got two eclipses coming out here. All right, so I'm going to introduce you to Jaden Stark and Todd McKinney to give the talk.
All right. Thank you, everybody, for coming today. I don't know if there's a
That's why they made them.
microphone.
The whole room is microphone. Yeah, the whole room.
Oh, is it? Oh, I didn't know if it projects that well enough.
Sitting on my radio.
Are y'all okay with the lights off?
Yeah. No.
Yeah, I don't mind that.
It's eclipse after all.
It is. So we're on Zoom too. Okay. Okay, thank you, everybody. So my name is James Stark. I'm an undergraduate here at the University of Alabama, Huntsville. And so, yeah, I'm a student here at UAH. I've been working for the Marshall Space Flight Center as a civil servant since January of last year. I'm also from Louisiana, and if you've read the news today, you know that being a civil servant from Louisiana, I'm having a very bad day today. I'm here to talk to you about a research project we've kind of started in preparation for the upcoming solar eclipse events that will be happening over North America. An annular solar eclipse in October and a total solar eclipse over North America in April of next year. So I'm going to try and go quickly through this with how the schedule is. So I'll get y'all out of here real quick. So our project's name is Saros, and Saros is exactly 223 synodic months and approximately that many days. It's just a cute term, but it's used to predict eclipses of the sun and moon. So it was the basis for our project acronym. And I'll breeze through this. This is based on an engineering design review with a lot of acronyms. So the dual eclipse overview. Let me move the Zoom overlay away. If that's even possible. Yeah, if I can get the Zoom overlay to go. That's fine. So yeah, two events will happen over North America. On October 14th, the Southwest will experience an annular solar eclipse. And on April 8th, 2024, we will see, of course, a total solar eclipse over North America. No, thank you. So these are two rare events, which won't be repeated until well into the 2040s, that we can use to conduct high altitude science as undergraduate students. So an annular solar eclipse versus a total solar eclipse. So if you're not familiar, the difference between the two, in both instances, the moon does go in front of the sun. However, for an annular eclipse, the moon's relative size to Earth does not completely cover the sun, so it produces this annulus effect. That's what we'll see in October. It varies, but just between eclipses, but that's what we'll see. And of course, a total solar eclipse is where the relative size of the moon does fully eclipse the sun, and so there will be a blackout over Earth during that period of time. So both are really cool events, and we'll get to see both of them in pretty quick succession. So I'm with the Space Hallmark Club here at the University of Alabama, Huntsville, and we've been conducting high altitude research for a while. In fact, we were at the 2017 North American solar eclipse. Our member here, Christopher Helmrich, was a part of this team up there. So that's cute. We want to continue that for the 2024 and 2023 eclipses. So in this presentation, I'm going to go over a project that we proposed. We're going to talk about the science objectives, the payloads and the instrumentation, and then our launch operations and our predictions. So science occurrence overview. Okay, so shadow bands, something that I've recently become familiar with. Shadow bands are these oscillatory light phenomenons that are found during a solar eclipse. They appear as these lines of oscillating light, which appears across the ground. I haven't seen them myself. Has anyone here been in an eclipse and seen shadow bands? So astronomers have observed them for centuries. It's just this thing that happens, and it's been theorized or really modeled as an atmospheric phenomenon. You can imagine, to me, how it's explained to me is that at the bottom of a pool, you might see ripples of light as light goes through a fluid, and Earth's atmosphere is a fluid. So the atmospheric scintillation hypothesis proposes that Earth's atmosphere is refracting the highly focused light of the eclipse corona, and that's what we see on the ground. However, recent high-altitude balloon experiments from the 2017 eclipse have seen oscillatory light phenomenons associated with eclipse totality at altitudes above 20 kilometers. So it's kind of interesting that we have this what's thought to be a primarily atmospheric-driven phenomenon existing outside of 90% of Earth's atmosphere. So that's something that we want to look at for our upcoming eclipse experiments. So here's a video of shadow bands for those who are not familiar with it. This is, I believe, in Arkansas during the 2017 eclipse. And you can see on this white canvas this very faint, smoky light oscillation effect. I'm glad we have the lights off right now, but you can barely see it. But as totality progresses, about 120 seconds before totality, leading up to totality itself, this oscillatory light phenomenon is known to occur. Kind of goes. And then, of course, you reach totality itself, and there is complete darkness. Yeah, it becomes more and more pronounced and then goes away. And then, of course, there's totality. So yeah, so we're trying to investigate this rare, unique, small window of time before and also following eclipse totality, where these shadow bands occur. Let me not watch that again. Thank you. Oh, no. There we go. Okay, so modeling eclipse shadow bands is based on different turbulent layers of Earth's atmosphere, particularly in the first 2 kilometers. These bands begin to form approximately 120 seconds before totality. So what we're seeing is that perpendicular winds are scattering the eclipse corona because they're modeled as seeing there actually be light that's around the moon as it's about to cover the sun. And so since atmospheric density and many properties change with altitude, we want to perform some in situ measurements of shadow band oscillation, size, direction, etc., at different layers in Earth's atmosphere as they occur during the upcoming solar eclipse events. So let's talk about high altitude shadow bands. So a group in 2017 showed a low frequency light oscillation effect, approximately 4.5 hertz, which is approximately kind of what you see in that video. It's not a very fast oscillation. It's a very pronounced, fairly slow oscillation, occurring at ground, but also from payloads at 20 kilometers. So yeah, so they had these sensors with these photodiode plates placed a known distance apart. And by looking at the difference across them, they could measure these light rippling effects. And so what we see, and it's kind of hard to read these plots, I hate sometimes when people make plots, is they're interested in this 4.5 hertz signal that persists around eclipse totality. This is my best way to try and condense this data. And so a lot of studies going into now what is happening between these two to where there'd be a correlation between when this signal appears and when this signal appears at the same time between 2 units on the ground and Earth. And of course, it goes away during the eclipse totality. So I'm not a physicist, I'm just an engineer giving this presentation. So we're here to try and investigate this ourselves. And so our shadow band experiment objectives are to characterize shadow bands throughout the first 2 kilometers of Earth's atmosphere, but also investigate potential light oscillations at high altitudes. And we want to collect meteorological data to relate that to the shadow bands in our investigation. So here I have an example of how the shadow band detector might work. As light oscillations pass over the light sensors, of course, we would get different analog signals. And by interpreting in the known distance between these sensors, we can try and understand the size, direction, and frequency of the bands themselves. I have that little animation. I don't know if it'll replay if I go back. But yeah, you're expecting to see a difference in an analog light signal if it were some sort of photoresistive device. So that's the theory of this instrument. It's repeating a study from 2017, but we want to do it at a much larger scale. There you go. So yeah, so there's 2 primarily ways that we could go about this, photodiodes versus photoresistors, but we're leaning towards a photodiode approach because of their fast response times. So yeah, there's different choices of photodiodes. Our best overall choice, there's these PIN avalanche types because they have improved response times and low capacitance planar diffusion. So in the same time, we're going to be analyzing Earth's atmosphere, so different lapse rates. So we're looking at differences in temperature, differences in pressure as we go up. So if we fly this experiment, we would of course have to have meteorological instruments. And at the same time, you have an instrument that's measuring some sort of light. So you need to characterize the dynamics of your line. So we intend to intersperse along our payloads inertial measuring units for measuring the orientation of this device, and also GPS units because you need to know its location relative on Earth. So this would be an example, the sensor package. If we had a sensor package and it's being affected by wind, we can measure the multi-axis movement and use that in our data calculations. And of course, we want ground-based measurements. So we're looking at a lot of different things. NASA is really interested in these gravity waves that are induced by the eclipse itself. So we'll have ground stations in our campaign looking at these and also providing ground references for all our meteorological data. And of course, we want video. So we're a student organization, we advertise a lot. So we love taking high altitude video. And high altitude video during the eclipse is very special. So that's something that we're investigating through our not investigating, but capturing through our flights or camera units on our lawn. So let's talk about the payloads and instrumentation. So we have 3 primary classes of payload. They support different experiments. We love our acronyms, but the purpose is so we can break up the cost. We want to have many sensors for measuring light, but we don't need the same functionality on all of those packages. So we're going to be separating communications and different experiments and different costs of sensors along 3 different classes of payloads, which we're going to go over. So the class A payload design that we've conceptualized is our primary payload. It's the most expensive payload and has all the data communications handling for the flight line. It also manages the flight termination system called DROP. DROP will be discussed in a later presentation at this conference. But also RTCs are GPS and all of our wireless communications. This kind of block diagram of our proposed thing, a dual microcontroller setup, talking to our cut down, but also to handle our cameras. Do this quickly. Class B payloads is a reduced form of the Class A payload. It has all the science experiments. It's lacking the flight termination and some of the wireless capability. But it also contains the shadow band experiment where we would have at least 4 photodiodes that would be in the visible light spectrum. Then a Class C payload is our most basic payload design, which would primarily be for capturing meteorological data, like for pressure, temperature, and also relative humidity. So let's talk about launch and recovery. So we have different teams. These were the objectives they gave me. So we have a team of students. We like to pretend that we're NASA. So we have a lot of people working in different facets of this project to engage them. So they're working on flying support equipment, ground support equipment. We create SOPs, standard operating procedures, all these engineering design criteria, principles, things. But yeah, so we launch balloons and we've been impacted recently by helium restrictions as an organization. So we try to reduce the number of individual balloon packages we actually fly. We'd like to fly a larger balloon rather than flying multiple balloons because it's just been really difficult for us as an institution because we cannot use hydrogen. We're not allowed to bring it to our launch sites. We're not allowed to use it as students. So we do rely on helium for all the work that we do. And it's something that we currently have to deal with. So for our project, we kind of tasked our group with how can we do as much science as possible within the altitude window that we want without sending up 100 radio sondes or 100 wind sondes. And so the process that we want to do is send up a very long, lightweight suspended line up to 1 kilometer, if at all possible, is the studies that we've been working on. A line that could be segmented in 2, but could be terminated at a low altitude. And what's this really useful for is that as you rise in altitude, your payloads are sampling, but not only are they sampling the delta as they rise, but of course, if you wanted to sample at 5,000 feet, you get multiple soundings over time as multiple payloads along the line cross this threshold. So we're looking at, and again, this is a very long line, but long lines in general as a means of characterizing the difference in shadow bands at 1 altitude versus 1 kilometer. Because if the literature suggests that it's purely an atmospheric phenomenon, we do expect that atmospheric variables are going to be the primary things responsible in the shadow bands themselves. So let's talk about our line. So you have your high altitude balloon, we have our flight termination systems. We have our parachutes, which are halfway between our line discontinuities, and of course, many micro payloads. suspended throughout this line, and our high visibility 1 mile visibility streamers that we are working on. So payload distribution, so we have multiple strategies. I just went over the whole ABC pattern. The reason that was important is because we're assuming that we're flying 100 payloads. That is what we budgeted mass for. That's what we limited them to. So every payload's not built equal. We're putting the payloads of the science that we need where we want them. So you can see there's multiple ways you can do this, and we're studying 2 different patterns. Can we alternate the B and C's at regular intervals where it goes B, C, B, C, or can you go in this dual setup? And so this is an example of kind of designing this flight train to be optimized for price and weight within our scope. And so we've looked at lines. You might ask, how much does a line that's 1 kilometer, how much does that weigh? And it doesn't weigh that much. There are actually many, many, many options if you're looking at something that's potentially compliant. So Kevlar, great option. We want minimal stretch. We also don't want that much cost, but we're looking at these lightweight tensile lines. We need to start characterizing them. We have a great material science presence on a campus, so we're going to be using their resources for characterizing different lines. We've begun doing it. We've bought a couple options, and we're going to be trying to do a small scale test on that soon. One thing we do have at our advantage is our designated release of payload device. So it actually utilizes a archery release trigger, which can hold hundreds of pounds of tensile force that can be released with a hairpin trigger. So that's very easily motorized, but it can hold much more mass and a much, much, much thicker line than a nichrome cut down, which of course has to use some sort of micro braid that can be easily cut through with a hot wire. That is not what you need with a device like this, because of course it's meant for archery. It's meant to hold a lot of weight and can be adjusted to release. So there will be a demonstration of this device. I'm going to talk about this device later. So let's talk about kind of, you're trying to launch this type of device. We want to deploy this up in somewhat of a controlled manner with guy wires, or not guy wires, of course, depending on launch range. But we would have this tethered and ready before eclipse totality, but we would deploy at the moment of eclipse shadow band occurrence, which would be 120 seconds prior to eclipse totality. You would release and sample as you rise in altitude as the eclipse progresses to totality and the shadow bands propagate across Earth, measuring from 1 to approximately 2 kilometers in the delta it takes to rise in 2 minutes with a 5 meter per second ascent rate. And then as the eclipse happens, you're in blackness, but when you come out of totality, shadow bands begin to persist again, so you are now at a higher altitude. You're essentially flying a tethered line, but not tethered, but you're sampling along a long span of altitude, and the data you collect at 1 altitude and the data you collect much later at the higher altitudes, around 5 kilometers, 6 kilometers, we believe are going to be very useful for our experiment. And then what we intend to do for landing a 1 kilometer line is to segment it at multiple points. And those segments themselves with centrally mounted parachutes would actually fold around the central pivot point. And they would end up actually quartering themselves as they land on the ground. We kind of call this our line folding descent ConOps, which is where if you have a centrally mounted parachute and a uniformly distributed load, that line's going to kind of fold itself. It's going to kind of halve. So if you're worried about landing incredibly long lines, effectively you can land it. And if we don't care about the condition of the sensors as they descend, we don't care what happens to them. We need them on the ground. As long as you effectively deploy a parachute, you can have a tangled mess on the bottom, but it won't necessarily have the footprint of an incredibly long line. That might be problematic. So let's talk about flight day logistics with our flight directors, Todd and Cindy.
All right. You think this is crazy? It is.
It is.
So the eclipse, it's a big event, right? Who here would want to launch a balloon in an eclipse? Does anyone have plans for that? Yeah, I bet. So we want to do more than just the shadow bands payload. We want to launch some other space hardware club payloads. I think Mr. Chris wants to launch his Helen payloads. Havoc, which will have a demonstration, is the thruster payload. We want to launch that. We want to do 2 actually, isn't that right, Jada? We have 2 of those flights. We're also a part of a NASA initiative called the NEBP National Eclipse Ballooning program, where we're actually launching, and we're going to try a live stream payload. So we're going to fly that, and we're actually going to float that, or we're going to build a float device. Of course, me personally, I call it the pod payload. You know, I got to fly a payload too. You know, I got to build something. So the goal is really, you can see this is actually solar flux. So that's what you measure from the sun. And the solar flux, if it was a perfectly clear day, your graph in time would just be, you know, straight up and down. But when you have totality, you have this dip. So the goal is really to launch either an hour before and or during the eclipse to be in that totality. We also want to do these smaller payloads. This is actually a partnership with the University of Alabama, a swirl team. They actually are interested in it's called the boundary layer dynamics of the eclipse and how a sudden removal of solar radiation affects weather in the bottom 2 kilometers. So they're probably going to come travel with us to the eclipse. So that'll be a good partnership. So it's just a little key. These are kind of this proposed idea. See, notice we could have payloads at multiple altitudes, right? And we're the shadow band payload we're talking about, it's just this small little circle. So you could put this on any payload and just have it up in the air, and as long as you recover it, you can have this giant profile in addition to the long balloon line profile. So if we want to look at shadow bands at higher altitudes, we'll have like my payload or Chris or Jaden's payload, which will have a little board on it as well. So we'll essentially get a whole profile. So of course, timing is going to be important. You can't mess up an eclipse launch, right? It's one event. It's either you make it or you don't, all right? And if you don't, you go home and cry because it sucks. So this is what I was just mentioning. Swirl is great. We're launching from Swirl yesterday. There's actually a guy who, if is anyone interested in a Swirl tour, he's actually going to give you all a tour of the facilities. If after you launch, or before the launch, you can see Swirl, all the vehicles we have. I know a lot of people might want to launch and get in their car and go chase, but we will have a tour available if y'all are interested tomorrow. So we can talk more about that tomorrow. So this is really neat. So if y'all have seen these, it's called a SKU-T. Meteorologists use them a lot. Think about it, if you're launching a balloon every 10 minutes, right, you can get really high resolution data, especially for an event during the eclipse. So this is what the Swirl team is proposing. They want to look at boundary layer dynamics, and they're looking at possibly doing 7 smaller soundings during the eclipse. And those are those radiosondes. If you want to come look, there's some radiosondes up here. They'll probably be launching. So this is also important, right? I'm a meteorologist, so I like to look at weather data. When you're launching a long balloon line, can you imagine what like a 15-mile-per-hour wind would do for a long balloon line at the surface, right? I mean, y'all have probably seen when you try to get your balloon off on a windy day, I mean, it can get a little crazy, right? So looking at climatologies and figuring out the best launch sites can be really important. What is the possibility or what is the probability that we're going to have really fast winds at where we're launching? That's important. So I recommend when y'all are looking for your eclipse sites, if you're going to do a balloon launch, look into the climatology, because you don't want to go somewhere where it's traditionally cloudy, like a lot of moisture, or it's traditionally windy, because it just makes your life more awful, especially if it's cloudy. Can you imagine? That would suck to miss the eclipse, right? So this is some examples we've done. We've actually run these model runs to see like where the jet is. This is during the month of April, where the relative humidity is for our launch site. So it's kind of neat. As y'all know, it's the summer. Winds can get weird, right? You go one way east and you come back west, right? Y'all ever seen that in the stratosphere? Yeah, it's really fun. Sometimes you can land it right at your feet where you launched because the winds cancel out. It happens. We've had weather balloon launches where you launch it and it lands 2 minutes down the road. It's incredible.
Or you take off going east and drive 25 miles, then have your land loom 12 miles west.
Exactly, it's weird. So, we do these climatologies and they're really, really helpful because it's determining where, we gotta get all this data back, right? So we're gonna be doing a lot of that. Okay, so I think I talked about this briefly in my talk, but I do a lot of high split modeling, so trajectory modeling. We've done a lot of work where what we do is we run trajectories from a launch site and we run thousands of trajectories, right? I want to create a probabilistic forecast to see where something might land. So this is an example, right, of, why does this thing keep coming back? So this is just a normal balloon flight where we're launching. These dotted lines are actually the path of totality. And you can see that for a full flight, this is going up at around 5 meters per second, bursting at 30 kilometers. We're in where we're choosing our flight. We are in, most likely, based off this probabilistic forecast, we're in the path of totality. So basically what I do is I simulated a balloon flight thousands of times from one point. When you do that over and over and over again, you can see, oh yeah, my balloon is most likely going to be in the path of totality the whole time. You can then sort that by, oh, well, the ascent, let's just look at the ascent, and let's look at the possibility of landing location. So you can also sort it by that. And you can see these dots up here. You're probably wondering, what are those dots, right? Those are actually cities sized by population, right? Because I don't want to land in downtown Memphis, right? So this actually shows the probability of like, what is the probability based off of all the past weather data the last 10 years that I'm going to land in a big city, right? Because if you look, all you do is you look at where your probability is and you look at those dots and you say, oh, you know, I'm mostly landing in rural areas. The dots are really small. So that's really nice, right? So we've done a lot of work with that to pick out locations. Here's another, this is actually for the cut down. If we were to cut down at 7 kilometers with the big, you can see it changes a lot. We went from drifting pretty far away in some cases to being in the local area. So we can fly a really long balloon line and be in a rural area and stay in a rural area. So really cool to see. We can also get the probability of our landing location. So we can like segment our recovery teams around a certain area to, you know, really nail down where it's going to land. So really great for planning. This is another one if we were floating. So you can see when you float, you go a little farther compared to this. You can see you're drifting into landing in downtown big cities. So kind of fun. So we also have been working on where, because we're using a cut down device, we set up a high split trajectory program that actually cuts down. It runs a model and shows you all the cut down altitudes and where you're landing. So if you cut down at 7 kilometers or 8 kilometers or 5 kilometers, you have a trajectory for all of them, right? So you can choose, oh, I don't want to land in these like mountains over here. I want to land over here. Let me cut down at 10, right? So you can do that using the meteorological device, which is really cool. So we set up a whole thing to do that. And we'll talk about the drop device later. All right. You want to come talk about this?
Yeah, I'll talk about the size.
Where do you want to go launching from?
We're about to talk about that. I was say, I don't know why this slide here, I removed this section for
It
GSC.
looked like old territory on the beard.
So 2023 launch location. So since we're targeting the Southwest, I've made a contact at the South Texas Regional Airport, which is a fairly decently sized airport in Hondo, Texas, which is southwest of San Antonio. And they have agreed to our launch operations. So we'll be there on October 14th. They're our primary site. We have a couple secondary sites, of course, due to weather, but our current plan is to go to the South Texas Regional Airport. They have very wide open spaces. And of course, the terrain around that area in South Texas, fairly flat, pretty nice compared to around here. 2024, I didn't have a choice. Our Alabama Space Grant Consortium office has contracted the Winthrop Rockefeller Institute, and they provide us our funding. So we were instructed to launch in Morrilton, Arkansas, which is not ideal, but it is in the path of totality. So I'm still working with them, but it's a nice sectioned off area with lots of wide open spaces for us to stage our operations out of. We'll probably be there with many other university teams, but there are secondary sites that we can go to, including Texas for both eclipses, because the eclipse path, of course, makes an X formation. And it actually goes through the city of San Antonio for both eclipse events. So San Antonio will probably be popular. So that's just kind of the launch site, brief overview. Conclusion, in summary, 2 solar eclipse events are rapidly approaching. We're still reaching our funding milestones. We actually have, this is an outdated slide. We've actually achieved all of our key funding goals. And our helium availability has been secured. Our traveling logistics are actually working out better than I thought. And of course, we're still working on our experience with launching longer and longer balloon lines. But overall, we have a very large team committed to this. Is just a small section of the team who I'm saying that put in like hundreds of hours to this project. This presentation was cut down from a 198 slide mission concept review. We cut out all the trade studies. I cut out all the engineering stuff, but it was hundreds of hours and work that was gone on physically in a lab, not just for presentation, but a lot of physical hardware has already come out for this project. But of course, we're students and we're all young. You can see all the bright, talented people here from UAH. So, but yeah, so that's it. I know we're kind of behind on schedule, but we came out okay. 2:35 is not that bad, but yeah, so we're open for discussion on the project. Yes, sir.
Do you know how many bits of A to D conversion you have on your photometers?
Sir?
You know how many bits of A to D conversion on your photometer?
Oh, so what's our analog digital conversion we're looking at? So I think we were actually picking up 16-bit ADCs is what we're looking for.
Shadow bands are only a few percent
Correct.
contrast.
Yeah. So actually in the back, Sam, you did the trade studies on the photodiodes. You became an expert on photodiodes in about a couple months.
Yes.
So I actually cut out which model we selected because I wanted to make the presentation shorter. But yeah, we're using a 16-bit ADC at least, or at least an 8-bit. No way we do like no, sorry, no way we go below. Sorry, 10-bit. 16-bit was our selection.
10 times expected.
The photodiode type that we're using, avalanche type, we're using 16-bit, and we have started. We have them in the labs right now. We've done a couple tests with 2 different versions that we're looking at the avalanche types. We've yet to put them in conditions that are similar to the shadow band phenomena, but we're working with the physics lab here to potentially get us a setup where we can simulate that environment.
Yep. We have an
so they're going to be spaced on a non-reflective PCB, 10 centimeters in either direction, or in each corner.
My point being is the noise floor of your system. Well, that's all your gains and losses will start right at that noise floor. And in my experience, if I could offer any advice of you to try to pay attention very closely, because you could lose the first 2, 3, 6 bits of resolution in noise. So, and that's something you can model.
Okay, that's awesome. Thank you.
We have an optical turbulence lab here at UAH who we're going to work with, which actually really neat. They haven't seen this phenomenon before, but they're interested in working with us. And so the optical turbulence, it's an odd coincidence that we actually have a large presence with that. It's from what I hear on campus. So we're going to be working with them with some modeling and simulation, definitely.
How long is that train again?
It is 3,680 feet long.
You really need to do some FAA coordination.
I have.
We're going to do that in Texas with flight plan patterns, the time that you got top dead, eclipsed. If it's over Dallas, Fort Worth, and you're taking up 7,000 feet of airspace, somebody's going to be PO'd.
Exactly. So I talked with the South Texas Regional Airport. We've talked about staging it from your airport and what we will do. And so we have some pilots in the club. We have some people who have worked in it. And so we are really working on the waivers for this actively.
Yeah, you need to take a look at their inflow and their outflow. Kind of.
Oh, yeah. The waivers and stuff. So yeah,
Okay.
that was a very early talk that kind of went on. And they actually, the more I actually put it in front of some of these people that I thought would be very upset about it, the more they're kind of okay with it.
Kind of okay.
Yeah.
Kind of, well, more so than I ever thought.
Okay.
Because I mean,
I just don't want you to hit the sticky wicket. Now we got more
Yeah.
egg on our face and more congressmen trying to. institute
oh, of
those.
course. And I mean, this started way before that. So that's funny you say that, because that really was kind of a concern.
I have a question to the EOSS group. How long is the Air Corps payload?
Sorry, sir.
The Air Corps payload that is based on?
No, the Air Corps is all coiled up and it's only a box that's
Oh, okay,
it's on the side.
not very long.
And of course, we're talking outside of what the Part 101 weight is.
Yeah, I'd be-
so
I'd be a little worried about power lines on the.
that is, oh yes, it is a concern, but it's a concern with every launch we've ever done. And
Unless you're in West Texas, then
our mitigation on our line folding was to try, the whole line folding concept came as a way to talk about how can we reduce the line's footprint as it descends. And so a 1/4 kilometer line is actually not that uncommon. We've seen people fly long lines. Landing a line that's 1/4 kilometer long, it's long, but it's not that long. And if you were to take two 500-meter segments and cut those in half, with the line folding idea, you would get 2 1/4 kilometer, 250-meter segments, which is long, but is not 1
The
kilometer.
trajectory modeling is critical, especially.
Yeah,
if
the
they're dropping
trajectory
boats.
modeling is
You can
critical.
choose where you want to land. I mean, you run all the models and you say, if I cut at 2.6 kilometers, I will land in.
And
we've done that before.
we've used this cut down system, this mechanical cut down system, reusable, completely mechanical system, and it has been beautiful for our efforts as far as releasing payloads and saying we want to terminate now. And we will talk about that and demonstrate that in a later talk. So this is also a key piece of tech that we kind of built up in preparation of saying we can stage multiple of these. We can cut into 4 1/4 segments that fold to 125-meter segments. You can put these and space them apart. And it's just, again, engaging a lot of people in a systems engineering mindset. We got a lot of people into this NASA engineering lifecycle, and I, of course, cut out over half of the slides from this presentation, this MCR. I mean, I guess the one piece I left was the acronym slide. And of course, I don't know, I don't have the original on this computer, but it was 198 slides, and it was this was a 70 slides. So this is the tip of the iceberg. You haven't seen our interface control documents, our requirements matrix, all the systems engineering stuff that we've kind of just wanted to tackle and engage ourselves as students, because of course we're a student team, and we just want to do cool projects and work with cool ideas. So that is the main purpose, and we've been given the green light by a lot of people to continue to do that. UAH has been very supportive of our group and everything we do, and all the other stuff we will do at the Eclipse. As you can see here, these are all separate research projects and separate balloons, separate from the Saros mission itself. So, is that it?